Yeah, well, thank you for having me. My name is Daniel Kunin. I'm finishing my PhD at Stanford and then starting my postdoc at Berkeley in the fall. And I'm going to be introducing kind of some of my work and previous work and my lab's work around the learning dynamics of neural networks. So the first 2/3 of my talk will really kind of start off where Jim's talk ended. And then the last third will be ongoing work, touching on some phase changes and things maybe more overlapping with what Dimitrios talked about in the last session. All right, so let's get started. And hopefully you'll understand what this nice graphic looks like or means at the end of the talk. Well, I might have to use this. I think the battery died. Okay, so as we all know, deep learning has, let me get rid of that, okay. Okay, you might just not get the top.
You can say, okay, to them, this meeting is being recorded.
Yeah, I don't know where my cursor is. Okay. There we go.
And this is
I think it's the battery instead. Okay, all right.
Yeah.
Okay, so as we all know and probably have experienced in the last couple of years, deep learning has truly revolutionized AI from computer vision to natural language processing to scientific modeling like AlphaFold. And largely speaking, most of these advances have been driven by increasing computation. Computation in terms of the length of training, the sizes of our data sets, the number of parameters. In fact, governments and billion-dollar companies are using these scaling laws to essentially determine how they invest in AI, kind of betting that just with more computation, they'll get more and more powerful AI systems. And despite all of this success, there still remains this kind of fundamental question, which is what are the principles governing a neural network's ability to generalize? So my work kind of has touched on what I think are two kind of prevailing perspectives in the field. The one perspective is this implicit bias perspective that essentially over-parameterized neural networks can memorize their training data, but it's the interaction between the architecture and the training process that biases them towards these simple solutions that generalize well. Examples of this from even early literature have been showing that gradient descent, if you train logistic regression with gradient descent, you always will be biased to this, with linearly separable data, you'll be biased to this hard SVM solution. Or that there are low rank or sparse or low entropy biases in, for example, matrix factorization problems trained with gradient descent. Or even there's been a lot of work on double descent or benign overfitting, which is kind of a completely new way of thinking about even linear regression, that you can be in a setting, the non-U-shaped curve, we could be to the right of this classical setting where there's some balance between bias and variance. And in fact, even if we have way more parameters than data points, we can still find ways to generalize well if we have the right kind of implicit bias or regularizer. I think there's another perspective which we kind of heard about at the end of Jim's talk, which is this feature learning perspective, that a neural network's performance depends on its architecture's ability to efficiently extract and compose task-relevant features from data. So examples of this is in AlexNet model from 2012, which was kind of the start of the modern deep learning revolution. People before that were using more classical ML methods to do image recognition. And then in AlexNet, they showed a massive improvement by using deep neural networks. And they noticed that in the first layer weights of their CNNs, they found weights that looked like edge detectors, or in neuroscience, we might call these Gabor filters. All of modern NLP is based off of word embeddings. And the first model to kind of determine how should we encode words into vectors is through a method called word2vec. And they noticed that there's kind of analogies in these vector representations of words, like king. The difference between the vector for king and queen is the same or similar to the vector between man and woman. And more recently, there's been a large push for what would be called maybe mechanistic interpretability of trying to reverse engineer trained neural network systems and finding kind of interesting features that these systems use. For example, if you train a neural network to do modular addition, it's been shown that these networks first encode the problem using kind of a discrete Fourier transform. They add the numbers together and then decode them. And so there's been a slew of works kind of looking at simple problems and trying to deeply understand them. And these perspectives, they're not different perspectives at trying to understand deep learning, but I mean, they're different, but they're not orthogonal, I would say. They definitely overlap. In some ways, you can think of really trying to understand a deep learning system as unraveling a pretty complex interaction of three ingredients. We have the deep nonlinear architectures that define neural networks. As Jim wrote earlier, in some sense, CNNs, transformers, MLPs, they all kind of have the same flavor of the architecture. There is the stochastic gradient-based optimization, like gradient descent or ADAM. All modern neural networks are trained in some first-order greedy way. And then lastly, there's these large, high-dimensional natural data sets. I would say that the implicit bias perspective in many ways kind of ignores the data set and really looks at the interaction of the architecture and the optimizer. While the feature learning perspective is kind of more inclined to look at the overlap between the architecture and the data set. I mean, and this isn't a rule, but this is, I would say, kind of more generally, they do take different perspectives. Today, I'm going to be trying to kind of jump between the two and introduce dynamics with data. Yeah.
But if implicit bias means spectral bias, then the spectrum of the kernel does depend on the data.
Yeah. Yes.
You can change the spectrum considerably.
Yeah, so there's obviously exceptions to the rule. I mean, there are works that do look at all the interaction of all three ingredients. I'm just saying kind of at a high level, like works, for example,
works, what have they done?
Yeah. And I think if you're looking at the literature, this might be a useful framing to think about how to think about theory works in deep learning. Yeah.
Would it be helpful to talk a bit about what's by features?
Yeah, I will be getting there. Yeah, definitely. Yeah. As for implicit bias, I probably won't be talking as much about it. So today, the two questions that are going to be driving the discussion are, first, 2/3 of the talk are what conditions enable feature learning and when and why does feature learning emerge? And we will discuss what I mean or even think about it as a feature. And then lastly, I'm going to be talking about kind of the mechanisms driving feature learning, basically what features are learned and why or how. Okay. So kind of informally, I'm not going to define it precisely right now, but let's just have an informal definition of what a feature is. You can think of it as any representation of the model that is used to make predictions. So for example, imagine we have data coming from these two concentric spheres and one class is blue, one class is red, and I want to somehow learn a function from that training data to separate the two classes. Well, I could use the coordinates, the X, Y coordinates in my data and their classes to do this task. Or maybe I would represent the data by looking at the X squared plus Y squared, and suddenly the task becomes quite a lot easier. So this is just meant to highlight this idea that learning the right features for a problem is crucial. And of course, those features will depend on the problem itself. So it does become a little bit of a philosophical question of, can we define features for a problem if we don't know what the data generating process is? Like it does become a little bit unclear. And I just want to highlight again that traditional ML methods relied on kind of handcrafted feature selection, usually using domain-specific knowledge. I mean, this problem is quite simple, but let's say you were trying to determine if this was cancer or not. They would use experts who were doing this problem to determine the right features to learn. And deep learning has really, or neural networks have really changed the game when it comes to ML, because they just kind of automatically learn good features. And as kind of, so if we want to understand when feature learning happens, a good place to start might be asking when it doesn't happen. And this is kind of throwback to exactly where Jim ended his talk, which is there is this very famous paper that Jim mentioned, and there was other papers at the same time that essentially show that if you take a neural network and you scale the width of the hidden layers up in a certain way, while keeping, there's some parameterizations and some specific things along the way, that the network ends up becoming linear in its parameters. So just showing here, if this is my network, where in Jim's notation, this would have been a phi, phi goes from some nonlinear function of theta and x to some linear function in theta, but nonlinear in x. And in this case, the feature map is the Jacobian of your function with respect to your parameters. So if you're looking for a more mathematical definition, this will be our definition of features, essentially, the Jacobian of your function. But I want to talk actually mostly about a different perspective on this when feature learning doesn't happen. That's not really at the infinite width setting, but it's when you change the variance of your initialization. So this paper here on the left came out about a year after, or maybe 2 years after the Jacob et al. Paper. And they showed that actually for a sufficiently wide neural network with a finite training data set, we can actually push it into a regime that is essentially the same, a neural tangent kernel regime, where it's acting linear in its parameters by simply scaling the initialization variance of these random Gaussian initializations that we usually initialize our parameters of our network with. There's some caveats here. In particular, they needed the function input-output map to stay 0 at initialization. You need it to be sufficiently wide, but broadly speaking, I think the idea here is that this isn't necessarily just something at infinite widths. Even at finite widths, we can see this trade-off between kind of turning on or off feature learning by just changing the variance of our initialization. So let's go through a little example that I think will make that more clear. And this is how, when I first learned about these works, this is kind of the example that really sunk in for me, made it clear for me. So, and this is actually figure 1 of their paper. So we are going to consider a wide 2-layer student ReLU network. Andre suggested I make sure everyone knows what a ReLU is. I don't know if, I think we all do, but essentially a ReLU is a nonlinearity that is just max of 0 and your input. And so you can think of it as this, if this is my input Z, then this is the output of my ReLU, okay? And this is probably the most common nonlinearity used in deep learning. And so we're going to consider a student network that has this 2 layers, and it's composed of many of these ReLU nonlinearities. So you can think of each of these, we'll call these hidden units like a neuron, and you can think of them as each implementing one kind of sub-function, and the total network is the sum of all these pieces, similar to how Jim talked about this morning. And the data that we're going to train this student on is going to be generated from another network, a different network that we'll call the teacher network. The only difference is the teacher network will only have 3 neurons, or far fewer neurons than the student. And so in this case, there's kind of a very natural, I now have a generative model for my data, and there's thus a very natural way to think about what feature learning here is. It's whether or not the student learns to align to the teacher neurons. Basically learns that I actually don't need 100 neurons to fit the data, I only need 3. So maybe I should only use 3, or I should collapse all my neurons to just 3, and that would be sufficient. So to visualize this, we're gonna just consider data in R2, and I'm going to plot the teacher neurons as each neuron here basically has an input weight, which is in R2, a vector in R2, and an output scalar. And so I'm going to just take the scalar and multiply it by the input weight. So I have A1 times W1 and A2 times W2. And the direction will be the direction of W, and the color will be the sign of it. I'm also going to plot the student neurons on the same setting. But now they'll be circles. So I have 3 teacher neurons, and I have, however many student neurons I have. The key thing I'm going to do is I'm going to initialize all the student neurons on some circle of a given radius. And I'm going to change the scale of the radius and see how that affects the learning dynamics, in particular, the degree of feature learning. So hopefully this is clear. The experimental setup is clear. On the top, I have my initialization scale getting larger, and on the bottom, or to the right, it's getting larger, to the left, it's getting smaller. And over here, I'm plotting the train loss. Let's do that again, because this took me a long time to make. So it deserves more time. All right. Okay, so some things that we might notice right off the bat is at large scale initialization, the student moved very little from where it initialized. This is kind of the same intuition that Jim was telling you with the infinite width setting. Here, it's not using infinite width. It's the same number of neurons in each panel. It's just that the variance is much larger. And as I move with a smaller variance, we see much more movement. We also see that, let's do it again, that for the small variance models, there's actually very little movement. At first, no change in the loss, followed by a sudden kind of explosion of movement. And then, that's aligned with these sudden drops in the loss. You might also notice that there even looks like there's kind of like 2 drops here. And that second drop seems to be aligned with like the movement of the neurons from this direction over. There's also another thing I want to highlight, which is that we see that in the small initialization scales, there really is this alignment of the teacher to, or the student, the circles, to the teacher, the dashes. So at small scale initialization, there is feature learning, and at large scale, there is less feature learning. This isn't just unique to the overall initialization scale. I could even change the relative scale between my parameters, so making either A larger than W or vice versa, and I can see kind of a similar behavior. In this case, they both start on a small circle, and it's just that in the right, when W is much larger, the dynamics are mostly radial, while on the left, we see kind of a strong directional alignment. Okay.
They should end up on the lines. The lines is the feature, right?
So it's hard to understand, right? So there's data, really there should be a third axis here, which represents the data. And in both cases, the model is interpolating the data. It's just that it interpolates it in very different ways. So in both cases, we go back to the loss here. All models end up achieving 0 training loss, but they get the solution they learn is very different.
So what does the meaning of the 3 lines then?
So the 3 lines are the teacher, the latent variables that generated the data. And what we're seeing is that the student ends up actually kind of, or sorry, the low initialization student is somehow learning that this data is actually coming from a low latent representation. In fact, I'm calling the training error, in this low dimensional problem, there would be no difference in the test error for the amount of data I'm using. But if we did this problem in high dimensions, essentially, learning the latent representation means you will perform much, much better.
In the graph of that arrow going to 0, which one? Which colors correspond to which?
Yeah, sorry. Blue, blue and orange it's basically going down is going right.
Okay.
Yeah. Good point to know.
Could you go back to where you explained what the plans were?
Yeah.
Oh, you did here.
Yeah.
So the teacher has 3
Three
neurons.
3 lines representing it. There is a kind of a scale invariance where it's like if you can align to the teacher in many different, you don't need to be necessarily the same radius as the teacher. Yeah.
And the points correspond to the student.
All of these different neurons. Yeah.
Do you scale up the learning rate, or another question, do you have to pay this price of time?
Yeah. So I'm not changing the initial learning rate in these 3, but if we were to make this problem extreme, yes, there is an optimization feature learning trade-off here. And you can really see it in this like long plateau. If we wanted to kind of have them all relatively on the same scale, we would need to think about how the learning rate interacts with the scale. Okay, so this is just to motivate, because I definitely want to keep going. I have quite a bit. And so hopefully, we'll see if we get it to all. All right, so this is kind of a similar thing to what Jim talked about. These different spaces where learning occurs in deep learning. So we can think about the parameter space, this really high dimensional parameter space. We initialize somewhere. Maybe we have a distribution if we're using Jim's language. And the architecture maps that point to a point in our space of possible functions. So that depends on whatever architecture we're talking about. Then we have some data, and we skipped the jump. And that data for that given for that given function on that data set X and Y, we get some sort of performance, let's say in training error, and we could also measure other things like test error. But on the training error, we kind of map backwards a gradient for the loss with respect to the function. You can think of this as a residual. We map that back through the Jacobian of the function, and that gives us a gradient in parameter space, which we use to update our model. And so we then perform updates through gradient descent in parameter space, which maps to some dynamics in function space, and finally dynamics in the performance space. And the key point here is that the map moving you between these spaces is the neural tangent kernel. It is this kernel of where the feature map is the Jacobian of your network, this time evolving kernel that depends on your parameters. And I think Jim gave some intuition, but another way to think about it is that it quantifies how one gradient step with one data point affects the evolution of the network's output evaluated at another data point. And so when there is feature learning, this kernel must change. So feature learning, I talk about it as if it's a binary thing. You either have it or don't, but it's not. It's a spectrum of feature learning. And in one setting, we have what's called lazy learning or kernel learning or the NTK regime, where essentially you have very little, if not no, feature learning. And then the other extreme, you have feature learning, and sometimes that's called rich learning. And I think I've talked to some of you outside, and I've had this conversation with others. There are many ways to do feature learning. I'm making it seem like it's just the one-dimensional, whatever spectrum. But really, there's only one way to be lazy. It's having your NTK not evolve. But there are many ways for your NTK to evolve, and thus there are many ways to do feature learning. But there are some patterns. So by definition, this is a different way of thinking about feature learning. NTK does not evolve in lazy or kernel learning, and it does evolve in feature learning. But there's some patterns that we've noticed. One is that lazy learning is associated with kind of large scale initializations, while feature learning is often with small scale initializations. In lazy learning, we kind of have exponential losses, if you kind of remember back to those really quick descents, versus things that have more plateaus and drops, kind of more sigmoidal looking losses in feature learning. So now we kind of have an idea of like when feature learning happens, but not really why. And I want to focus on why small scale initializations and sigmoidal loss curves are related to feature learning or the emergence of features. And to do this, I'm going to consider a very minimal model, a simple model. I'm going to consider a single linear neuron. So we have some input in RD, mapping it to R, but through this first vector of weights W, then we just multiply the representation here by A, and that gives us the output. So our minimal model is just going to be this single linear neuron. We're now going to dive deep into this model. So this is a good time. We're now going to get kind of specific. So this is a good time if there's any high-level questions. Great. Yeah, let's keep going. All right. So linear networks. Why do we care about linear networks? Aren't all linear networks just the same as linear regression? In their expressivity, that is true. All linear networks are linear in their input, but they actually are nonlinear in their parameters. So their dynamics are still quite complicated. You can see rich and lazy behavior, you can see nonlinear behavior, and so they're good settings to try to understand deep learning while still being analytically tractable. And there's a long history of using linear networks to study deep learning systems. This is just a few. There is one thing, though, that all of these all of these linear network analysis share, and that's that we see there's this symmetry in the parameterization of our linear network because of this. We're just multiplying let's say our second layer weights by our first layer weights. That means that we could always take our first layer, W, multiply it by some invertible matrix G, and multiply A on the right by the inverse of G, and nothing would change in the input-output map of our function. So we have this kind of symmetry under the general linear group of these invertible matrices. And the implications of this have been used in all of these analyses, and they have some pretty strong implications. For one, no longer is a minima of this, let's say we're doing mean squared error, we know that eventually AW should learn the OLS solution. No longer is the solution a unique point, but rather it's going to be kind of a manifold of minima. Additionally, there's a strong relationship between the gradients of A and the gradients of W, and this is pretty easy to see just by chain rule. And lastly, just using that property that holds throughout all of training, any A and W, that means that the dynamics of this quantity here, this difference in kind of quadratic terms, A transpose A minus W, W transpose, this matrix is actually constant through all of gradient flow training. And this is really the key property used in all of these analyses. And this idea that like there's a symmetry in the system and that led to a conserved quantity under the dynamics, that's not unique to linear systems. That occurs all throughout deep learning. So for example, in the weights immediately before a softmax layer, softmax has this translational invariance, and we can thus shift the weights without respecting the symmetry, and it leads to a conserved quantity through time. The lambda here is representing regularization. I'll say something about it in a second. Weights immediately before a normalization layer have a scale symmetry, and they thus would have a conserved quantity on just their norm or of those weights. And this rescale symmetry is not just unique to linear networks, but also occurs for ReLU networks or anything that is homogeneous of order 1. And okay, you might then be saying, okay, that looks flat and not moving, but these are all moving. And in fact, it's not a perfect conserved quantity. Once you incorporate the learning rate and the stochasticity, you get kind of a broken conservation law. So only under gradient flow will it be actually conserved. And really, I mean, you're all physicists. By the way, I'm not. I was like the one person or second person over there who is more on the computer science side. But I work with all physicists and I've learned a lot from them. And really this idea, this relationship between the symmetry in our architecture and conserved quantities under the optimizer or under through training is really a version of Noether's theorem. The key thing is you have to actually understand it perfectly, we'll have to actually represent gradient dynamics with a Lagrangian, and then you get then you can understand what the Noether charge is, et cetera, et cetera. So if you're interested in this, there's definitely a bunch of works to explore this. All right, so back to our minimal model. We have a single neuron trained on mean squared error by gradient flow. These are the dynamics, our gradient flow dynamics for A and W, our two parameters. A is a scalar, remember, and W is a vector. And as I just explained, one of the key things that we will use is that there is a conserved quantity in these dynamics. In this case, it's the difference between the square value of A, which is scalar, and the squared norm of W. And so wherever we initialize our dynamics, we're now constraining those dynamics to being on the surface of some high-dimensional hyperboloid. And so I'm just visualizing this in R3 here, but we have, there's a key point here is that the sign and magnitude of this thing will change the geometry of our dynamics. So when delta, this conserved quantity, is less than 0, we're on this kind of single-sheeted hyperboloid. When delta is 0, we're on this double cone. And when delta is greater than 0, we're on this kind of two-sheeted hyperboloid. What are the other, so this, I think you guys can see the hyperboloid. The color is representing the loss projected onto that surface. What are the other objects in this visualization? What I'm showing here is AW will eventually go to the OLS solution, beta star. The product of A and W needs to go to the whatever the minimum is, beta star. But there is a symmetry, again, between A and W, meaning the minimum is not just a single point, but really a manifold of points, which are the red hyperbola here. And then similarly, any initialization of our parameters, A and W, I can move them, I can change the parameterization or like what surface they are on without changing their product, beta 0. So that's what this gray hyperbola is. There's some other really critical points in this picture, which are there's saddle points of this loss. First, it should be clear to see that if I make A and W both 0, if I make all my parameters 0, then these dynamics cannot move, and that thus is a critical point of the dynamics. But it's not a minimum; it's just going to be a saddle point. So we see that here, right here at where these two cones intersect. There are other saddle points where I make A 0, but I make W orthogonal to beta star. In this case, this will be a critical point as well. If X transpose X is whitened, but let's just ignore that. Okay. Yeah.
Where does this conservation
This conservation law is coming from the symmetry between A and W. This idea that I can scale W up, scale A down, and nothing changes in the function. And the way you might see that here is that the dynamics of A are proportional to W, the dynamics of W are proportional to A. So if I multiply W here, and I multiply A here, you see that the right-hand side of both those equations are the same. And multiplying W here, taking chain rule, that's the dynamics of the norm. Multiplying A here, that's the dynamics of this thing. So if these things have the same gradient dynamics, when you look at their difference, that thing has a gradient dynamics of 0, so it's conserved.
What is particular to gradient descent?
This is particular to gradient flow, but this was kind of the motivation here. It's not particular to linear networks. This is true all throughout deep learning, in fact. There's always going to be, if you have n neurons, you often will have n conserved quantities. You might have n squared parameters. So it's not like it doesn't make the system solvable. In this case, it makes it solvable, actually.
And if you start to do a very different kind of learning, not with gradient descent, then you wouldn't have this, right?
So you have something, you can get more into it, and we can talk about this offline. But for this talk, I'm only ever going to be talking about gradient flow. But if you're using pretty much any gradient-based optimizer, there's something similar to a conserved quantity. It's not exactly the same. It's not exactly conserved, but it's quite similar. So yeah, I kind of already said this, but if we assume our data is whitened, our covariance of our X is whitened, we can actually solve the gradient dynamics exactly. You get this coupled Bernoulli and Riccati ODE, but it becomes solvable. But what is the kind of the change of variables I'm using? Rather than tracking A and W, I should track the norm of A times W and the angle between W and the solution. So by just tracking these two quantities, the dynamics become solvable in whatever dimension we are in for our input. Of course, there's a very big limitation of this assumption here, which is that eventually all networks, all settings of my initialization will converge to the same point or the same solution in function space. So really, when we talk about feature learning in this minimal model, we should be thinking about how does the MTK change along that trajectory, okay? So yeah, we can, given that we have solvable dynamics for the system, we can then look at the dynamics of the kernel. And one thing we'll find is that when delta is very large, essentially there's no change in the kernel throughout training. And one way to kind of intuit this or think about this is that as I move up this gray hyperboloid, which is all my similar initializations, I'm only changing delta as I go on this hyperboloid here. As I go up, I'm essentially getting closer and closer to the red hyperboloid, which is the minimum. So essentially one way to think about lazy that we already talked about is you're basically initializing at a minima of your loss landscape. So thus you don't move very much in parameter space. So you don't really change much in your kernel. In this setting, there's two ways to be rich, either when delta is 0 and you have small norm, or when delta is negative and you initialize kind of orthogonal to the solution. In both of these cases, what's happening is you're actually initializing close to these saddle points. So the big picture, if you just ignore it, if you just zoned out, you probably didn't have enough coffee and you're tired. The thing to think about, the overarching thing to remember here is that one explanation for moving between rich feature learning and lazy kernel learning is that in a kernel learning regime, you are initializing close to a minima, while in a rich regime, you're initializing close to a saddle point. And this explanation you can find this explanation in many different places, but I like this paper in particular by Jacot et al. In 2022, where they look at the dynamics of deep linear networks with some width. They initialize every parameter with some power law in the width, and they observe a phase transition in the degree of feature learning as they change the power law with the width scaling to infinity, where essentially when the variance is very large for all their parameters, and they have to do some stuff to make sure that the variance of the function doesn't explode and the expectation of the function is still 0. But what you find is that in this regime, when gamma is less than 1, the variance is very large, then you are in a kernel regime or an NTK regime and your initialization is very close to a minima and very far from a saddle point. Conversely, when gamma is very large, greater than 1, now your variance is very small. You're initialized close to a saddle and far from a minima. And this is what they conjecture is called this saddle-to-saddle process. And then kind of right in the middle, mean field limit here, when gamma equals 1, you're actually kind of equidistant between saddle points and minima. So this paper was really trying to highlight this regime. There are many works on this regime. Jim talked about that. There are also many works here. And there's, at the time in 2022, there were not so many works in this extreme regime. And in this setting, they conjecture that in this vanishing initialization limit, gradient descent visits a sequence of saddles, in this case, each corresponding to linear maps of increasing rank until reaching a global minimum. And they showed that what they see in the kind of loss plots, these kind of saddle-to-saddle performance in their plots, where you have these long plateaus followed by sudden drops, so on and so forth. And this observation isn't just in linear networks. You can find this in two-layer ReLU networks or intentionally transformers. And so there's a lot of reason to believe that in this extreme limit, where in fact actually training this practically gets quite difficult because of this relationship between the initialization scale and the learning rate. But you can still find these kind of stepwise performance curves. Okay. There's another way that we could think about our minimal model. Rather than thinking about the dynamics of A and W in parameter space, we might consider the dynamics of beta their product. Okay, and so this is kind of back, zooming back out and remembering that deep learning is about looking at dynamics in different spaces. This is about thinking about the dynamics in function space. In this case, our function is just represented by beta. You could derive this ODE for the dynamics of beta, and what you can, this looks ugly, just call it M. And what you see is that essentially the dynamics of beta look like a preconditioned gradient flow. So essentially you're doing gradient descent on the loss, but preconditioned by this matrix M. And it happens that actually this matrix is the same matrix that defines the kernel. So the nice aspect about this type of analysis is that we're not going to actually try to solve these dynamics. We're just going to try to think about how M changes. And in this case, we don't even need X transpose X to be low rank, because we're just thinking about how M changes. But a similar kind of change of variables could be used as we did in the parameter space interpretation, where rather than looking at, remember in parameter space, we looked at the norm and the angle. Here we could look at kind of the change of the norm of beta and the direction of beta. And what you'll find is that as we change delta, the relative speed of these two things changes. So in some settings, essentially the norm moves very fast and the direction moves very slow. Maybe not important to actually look at this exact plot here, but just understand this idea that by changing the initialization, I can either make them move kind of at the same speed, make one move faster or one move slower, so on and so forth. Okay. And so this is an alternative way of kind of understanding this difference between rich and lazy, but from this perspective, this function space perspective, where in a lazy regime, essentially, it's the radius that is moving the fastest. And the directions are moving slowly. While in the rich regimes, these are two different rich regimes, it's really the direction which is very fast and the radius is very slow. This kind of interpretation can also be used for answering implicit bias questions. In this case, saying what happens when we have many solutions? Among the solutions, which one do we converge to? Again, don't need to look at the specifics. The key thing to understand is that the initialization either encourages you to align to the minimum norm solution or preserve your initial direction. So this would be lazy and this would be more rich, something along those lines. So this perspective on the feature learning spectrum is that lazy learning is when you have fast norms and slow directions. And in this case, you can think of this as the network just tries to fit the data, period. Just instantly tries to fit the data without really changing its representation of the data. While in the feature learning perspective, there is a slow norm and a fast direction. So in this case, you find alignment of the neurons aligning to something in the data without changing anything in its prediction, followed by a fit. So kind of an align process, then fit. Again, this perspective can be found in the literature. I motivate it in this minimal model, but you can find this in the literature, and you can, in fact, this early paper from 2018, before the neural tangent kernel was even written, described this in a really simple problem. Basically, they had 5 data points, 1, 2, 3, 4, 5. And they're training a wide network to take in data in R and output data in R, in this case, predict these 5 data points. And as they make the initialization really large, they see this kind of squiggly line interpolating the data. And as they make the initialization really small, they find that the neural network kind of just piecewise interpolates these 5 points. And they make this observation that these ReLU kinks, or these kind of the points where there is a kink in the dynamics, moves while the training loss stays approximately constant. They essentially align with each other. So they're aligning to these data points before the model even fits. Subsequent studies have used this idea of distinct alignment and fitting phases to study more complex models. Okay, so now moving back to that picture that I left at the beginning of the slides, I hope this can kind of give you this idea between either just moving fast in norm and direction is slow, just essentially fitting the data, gives you kind of a picture, an internal picture of what lazy learning could look like, where I have these 8 data points, and essentially this function, this surface here is my neural network. And it's basically just moving up and down to fit those data points, but not moving its kind of representations, in this case, these cones, which represent the activation patterns of the hidden neurons. While on the left, we see this feature learning or rich learning, where there's a phase of kind of realignment, where you see that during that phase, the input-output map is flat, and the network is realigning to something in the data, followed by some fitting phase, resulting in what looks like this kind of origami-like shape, that really, you can think of it as the generalization of that previous experiment to 2D, where now I have, I'm basically piecewise linearly interpolating these 8 data points. So, great. So big picture, I started this talk by really trying to talk about what conditions enable feature learning. Basically, when and why does feature learning happen? And I focused on how we could talk about changing the architecture, but I want to think about, for a fixed architecture, how can I change just the initialization to either influence feature learning? And we saw that small scale initializations, that essentially is when the NTK evolves, and that's when feature learning occurs. And why? Well, there's 2 different perspectives I discussed. One, you could think of it as in parameter space, feature learning is happening because you're moving from one saddle point of the loss landscape to another, kind of jumping between saddle points. While an alternative way is to think that there's kind of some fast directional movement and slow norm movement. So the fast directions is allowing you to align to certain properties in the data, but without changing your input-output map. Okay.
Would you say the small scale initial division is a necessary condition? Because AlexNet wasn't initialized, I think, with Greenfield scale MUP, and it still learned the more filters. So I think that the amount of data is also a driving force.
Yeah. I think another big impact here is that as you go deeper, the scale of your initialization does not actually need to be that small. So depth plays a role here in terms of allowing that initialization to actually be quite large, while still keeping you close to this saddle point of the loss. So yeah, it's definitely yeah.
Why do you think that helps large initialization?
Why do I think depth helps large initialization? So I mean, simple idea, just x to the L, make x just slightly less than 1, that thing gets quite small. So it's basically that alone. We can talk about that in a more specific setting, where essentially, if, like, for example, if I took my minimal model, let's see where it is here, and I just added 6 layers of scalar multiplication here, and I trained all of those parameters with gradient descent, I would not need to push. I could get the same functional dynamics with a much with an initialization much more kind of regular. So that's why.
But the outputs would be very small.
Yeah, that exactly. The outputs would start. I can make them start at the exact same place in function space, but have dynamics by just changing depth here. I can have the dynamics move it more to rich learning. There's other obvious aspects of why depth helps, I think, in terms of neural networks. It's not just about getting you more into a rich learning. It allows you to have this kind of hierarchical composition of features, which I think for natural data sets, people believe that most natural problems really are quite hierarchical in nature. So I think that's another reason why neural networks have used depth. Most of my analysis is always going to be stuck to these 2-layer settings, and especially in the next talk, and that's really a limitation. It's something to think about.
So,
Yeah.
when you say small scale or large, this is set by the data, by the amount of data.
So what I mean is that we often initialize our neural networks as Gaussian with some variance. Yeah. So if theta I is just one parameter, it's usually initialized mean 0 and some variance. And I mean the scale of that variance. No, compared to other settings, right? Like, I mean, that's the point. Is like we initialize them. There's usually like these different special initializations to make things work. For example, like a mu-p initialization, as was asked by someone else. So in all these experiments, what I'm doing is I'm just saying, if I make this bigger versus smaller, how does that change the degree of feature learning in these two experiments? Yeah.
Understand that, but just not to
Most of the time, the features are also normal. The input features are also normalized to be.
You're asking compared to what? So there is, for example, standard practice, we could say. But no, everything I've been talking about is just if I make this larger or if I make this smaller, how does that change the dynamics in function space? Will that make it have more or less feature learning? So if you want to compare it to something, you just do this twice. One where this is large, one where this is small. Now we're comparing these two things. Yeah. Yeah.
So I have like actually 2 questions.
Yeah.
So would you say like if you have large scale initialization that goes into like overfit instead of like in small scale, you get like really generalized trains.
Yeah, I mean that's one way that you could think of that. Like here, you could imagine that essentially lazy kernel learning is kind of overfitting. This is occurring at large scale.
And I also have one more question.
Yeah.
So we were like assuming that we have like linear transform symmetry in this linear because between like A and W.
Yeah.
Then if we have like activation function, then we don't really have that symmetry anymore.
Mm-hmm. Yeah. So, ReLU will still have that type of symmetry. ReLUs are piecewise linear and they're homogeneous. So in fact, any homogeneous nonlinearity, by homogeneous, I mean you scale something you scale the input like Z, and then the output scales by some power of that scaling. Yeah. So ReLU will have that. In fact, I think maybe more importantly though, any nonlinearity, so we can visualize a nonlinearity. So you'll see this in literature where like maybe it'll look like tan H is this, and ReLU was this, and maybe square like that, right? Square. Intuitively, I think any nonlinearity kind of going through the origin is effectively at very small, when Z is very small, observes this kind of symmetry.
But if you have like large scale training, you kind of lose.
Yeah, you would lose that. That is going to be the conserved quantity, or actually this property is going to be something really critical for this next part of the talk, where I want to talk about what mechanisms drive feature learning in the small scale regime. And I'm going to be using this idea of homogeneity quite a lot. But yeah, in terms of my description of why at large scale you observe feature learning, the minimal model requires that conserved quantity, but a more general setting, you can still get that same idea of moving you towards a minima or moving you to fast norm dynamics without using that conserved quantity. That was just for the minimal model. Yeah.
Thanks. Just remind me about the nature of these saddle points again. So,
yeah.
So that I'm going saddle to saddle. You say they were each associated with a linear length of increasing length?
Yeah.
Okay.
Right. So, well, in the linear network, but that's a great segue to the next part of this talk.
Then,
great. So we kind of have this idea of now basically the goal of this next part is I'm going to be introducing some new work that I'm currently working on. And I'm really interested in trying to kind of understand the mechanisms that are driving feature learning. Basically, what features are actually learned and how. So for a general problem, we know in this, if you want to just zoom out again, what we know about feature learning is that the loss landscape, the loss kind of curve through time looks kind of piecewise linear. It looks kind of like a staircase or a set, yeah, like this. You have periods of long plateaus followed by drops, so on and so forth. And this is kind of associated, you can think of this as associated with being at a saddle point and then going to another saddle point, going to another saddle point, and so on. And so one thing that we want, if we want to understand feature learning deeply, we want to have kind of a theory of feature learning, the same way we have a theory of kernel learning or lazy learning using the neural tangent kernel. Now we want a theory of feature learning or extreme feature learning. We should be able to predict these loss levels, and we should be able to predict the jump times between them. But that doesn't really tell you what these saddles are associated with. So if we want to understand what these saddles are associated with, one way to think about that is, can we determine what these fixed points of the kind of directional alignment is in function space? That's one way to think about that. And so in the linear network, it was like, oh, each of these saddles was associated with a linear map of one more rank than the previous one. So yeah, so we're going to be kind of I'm going to try to propose a idea for how maybe we could think about answering both these questions.
In the plot levels, what kind of data that you see? You need some hierarchical data?
Oh, to see this kind of this, yeah. Yeah, so I mean, that's a great point. You won't always see, I have 6 years just made up. You might have one, right? I mean, you should have at least one. Otherwise, there's no signal in your problem, right? Otherwise, you're just flat the whole way. But yeah, the number of drops that will depend on the data set and the problem. And this is, again, back to kind of this idea here. In many ways, this first part of the talk, I didn't even have to think about the data. I wasn't really, I talk a little bit about it. It's usually by, for example, the minimal model with just what is the OLS solution. But I'm not really thinking much about the data. This second part of the talk is really going to depend on the data set itself. Or the theory will depend strongly on the data, is another way of saying that.
Yeah, we have like emergent behavior exactly on top of, let's say, emergent that we have.
Yeah. How many drops will depend on your task, will depend on the data. And so you might only have one, you might have many more. Yeah. Everyone, is this any other questions? Because I'm actually good on time somehow.
Maybe I can ask connecting to the previous one. So this feature learning where you're saying there, it goes in a certain point direction. Isn't that supposed to be? I don't know. Like it looks like it should be the phase transition curve where one of the SVD components increases or something like that. Or is it...
Yeah. So first, maybe you're thinking about dynamics of linear networks. Yeah. So we're definitely going to talk about that. Yeah. Okay, so I'm going to try, this is an ongoing work between people in my lab at Stanford and folks in the lab that I'll be joining at Berkeley. And actually, I live in Santa Barbara. So so also some folks from Santa Barbara. And essentially the TLDR of this work that is not done is that we're going to kind of conjecture that 2-layer neural networks with a vanishing initialization alternate between a maximization phase and a minimization phase. And that's going to drive essentially this saddle-saddle process. And what I'm going to do is I'm going to first kind of introduce the framework in general for these 2-layer homogeneous neural networks. And then I'm going to look at 3 specific cases of where we could apply this framework to actually get predictions for the loss levels and the jump times. And 2 of these cases will really be actually kind of unifying existing works in the literature. And the last case is a setting where I don't think there exists any analysis. So trying to kind of show that this framework encompasses previous things, but also provides maybe a lens or a tool to look at new things. Okay, so there's going to be many steps of kind of the motivation for this idea, but I actually think it is quite natural. So, but stop me if you have any questions. All right, so we're going to think about two-layer homogeneous neural networks. So first, we're just thinking about a network that looks like a sum of these neurons, just like before, where it takes in input from RD and outputs input in RC, let's say. And the nonlinearity is any nonlinear, you can think of it as linear or ReLU or square, but basically any nonlinearity that observes this process. If I take my input and I scale it by alpha, it's equivalent to just taking the alpha and scaling on the outside of the input of the nonlinearity, okay? So you can think if sigma is the identity, then that's clearly true where kappa would be, I guess, 1. No, yeah, 2. Okay, does that make sense? If this was square, kappa would be 3, and then that would also work. Okay. Say that again.
One-dimensional.
Yeah, whenever we talk about nonlinearities in deep learning, a nonlinearity is always going to be a map from one dimension. Oh yeah.
So then this is just you're like stacking together two or exponential. That's AF stuff and DF stuff. I'm going to rate. That's the only way.
Okay, so this is an example that would be homogeneous. This is an example. If this satisfies your definition, then I'm on board. This is an example.
And then you can like have different for negatives and positives. That's
Uh-huh. Yeah. And you can also allow for, I mean, that's basically any kind of polynomial that goes through the origin. Yeah. And
any monomial.
Yeah, any monomial you can, but again, I think that this assumption isn't actually going to be that strong because I think any nonlinearity kind of going through the origin here, when we're talking about small scale, will kind of satisfy it. Yeah. Okay. And then just to be clear, every neuron is represented by some parameter vector, which is the input weights W and the output weights N. So we just concatenate those together. So every one of these little subfunctions here, these little neurons, has a vector of its own parameters. By the homogeneity of our function, or of all these neurons, we can express the full function as kind of like this norm-weighted sum, where kappa is the degree of that monomial, like you said. And I'm now normalizing my parameters so that this function here only depends on the direction of my parameters. And out here, there's some norm that scales that contribution from that neuron, and then I sum it all together. And a key thing to notice from this kind of, once you do this is, or actually just for these two-layer networks in general, is that they can only interact through the residual, which is the gradient of loss with respect to the output, right? So for mean squared error, the residual is just the difference between the labels, y, and that function's prediction. But in general, for any kind of loss on the output, the gradient of the loss with respect to the output, we'll call that our residual. That's the only way these neurons interact because that's where they can see each other, essentially. Does that make sense? And so one thing we noticed is that in this vanishing initialization limit, we'll get, and I'm not going to show, but I just maybe accept this from the previous motivation, that the norm will move very slowly and the direction will move very fast, and this has to do with this homogeneity that we're obtaining near the origin. And what it means is that in the beginning, obviously, if theta is 0, the output of my function is 0, and so f will start 0, and my residual will start as just y. But it will stay like that for a long period of time, because if these norms are not moving very much, it doesn't really matter what happens to my function. It doesn't matter what the directions do. All of these things are weighted by the norm, and the norm isn't changing, and it's staying near 0. So I'll have this period of time where my residual stays kind of constant. And an important thing to note is that it doesn't depend on any of the neurons. Okay. So this is the first thing we're going to think. We're going to propose this this function, which we call the utility. Maybe like overly verbose for what it is. It's literally just the inner product between the expected inner product between the function, the output, for each neuron and the residual, whatever that residual is. And the reason this thing is important is that if we actually express the dynamics of the direction for each neuron and the norm, we'll see that is this normalized utility that is kind of driving the dynamics. So the important thing to note here is that the direction of my parameters is basically driven by projected gradient descent on this normalized utility. So you can think the utility is defined over the sphere in R M, where M is the number of parameters for each neuron. And essentially the direction of my parameters are trying to move to regions where the utility is large. And meanwhile, the norm is being driven by just the kind of total utility observed as along that path that the direction is taking. Does this make sense? And we have multiple neurons, and again, remember, because the residual, it doesn't depend on the neurons, this is all happening independent from each other. So each neuron is doing this process independent of the others. But this whole thing breaks down as soon as one neuron becomes O of 1 in size, right? This whole thing depended that the residual was constant. And that only could occur if the norms of my neurons were small. So we want to solve for essentially the time when the first neuron, we want to solve for each neuron, we want to figure out when will it essentially become O of 1 in size. And then we want to figure out what is the first time one neuron becomes O of 1. And that's essentially an estimate for how long this process could occur.
And O1 can be 1 over the number of neurons.
Yeah, we can, yeah, exactly. This is definitely something, your question is getting at a very good thing that I'm also been kind of struggling with and thinking about a lot, which is, right now I'm giving these high-level intuition about how my thought process, but thinking about actually the number of neurons is a very critical thing. Thinking about the kind of size of the data is also a very important thing, and I think there is a little bit more complexity in here. But broadly speaking, it's essentially that, yeah, let's just think about the time when a neuron becomes O of 1, and the key idea is that because the norm is just driven by this kind of accumulated utility, or the integral of your utility along this path, you can think of it, you get kind of an expression for that time just in terms of that accumulated utility and your initialization norm. In the case where kappa is 2, it just becomes this kind of, yeah, essentially the dynamics here are basically exponential, and when kappa is 2, this ODE can just be solved, an exponential ODE, or an exponential solution will solve this. When kappa is greater than 2, you get some sort of power law, and that's how you get these two different kind of expressions for this jump time. So this tells us essentially how long this assumption of the residual being constant could last, or the minimum time it would last. At some point, one of the neurons has to explode, at which point we need to change our process. So one thing we think about is we partition all of our neurons into a set, a dormant set and an active set, where the dormant set is still small in norm, the active set is not small. So we have a neuron that has now left the dormant set and become active. And the active neurons, they're all aware of each other. They all are large, and thus their residual, as they change the residual. So all the active neurons are kind of collectively coupled in their dynamics. And they all move very quickly because their norm is large. So going back previously, we saw that the dynamics were always proportional to the norm. So because their norm is large, they all move very quickly. And so essentially the active neurons all work very quickly to minimize the loss, restricted to just that active set. Once that active set equilibrates or reaches some critical point, then there will be a new residual. We'll then pass that residual back to the dormant neurons, and they will go through the same utility maximization process, but with this new residual. And that residual is simply just the labels minus whatever function the active neurons collectively create. And it's important to note that this process actually, in some sense, gives you a critical point, a saddle point of the original loss. If I have a critical point of the restricted loss, then the critical point where I have my my whatever those are for the active neurons, and then 0 for all the dormant neurons, that is a critical point of the unrestricted loss. That's a saddle point. So this process then will repeat back and forth until either all the dormant neurons there are no dormant neurons, or the residual is 0. Yeah.
How do you get a complete contiguous? For example, if you have many neurons and they're all controlled, maybe just one neuron to express your target function.
Yeah.
Then the largest active that would the feature learning to express your data set. So how do you actually distinguish between number of different neurons that must be activated?
So the point here is this is an iterative process where we start with all of our neurons dormant, and the idea is that all the dormant neurons are independent of each other, always. When they're in this dormant phase, maximizing their individual utility, they are by definition independent and decoupled. We then try to figure out which is the first one to explode. So in your case, you said it's the one that's the largest. Well, it might be. At the beginning, it probably will be. But maybe at the third round of this process, it actually might not be. It's a little bit more complicated. But the point is, in this maximization phase, everything is decoupled. Something enters the active set, all the active neurons are coupled. There's no way to uncouple them. But once those active neurons equilibrate, they create a new residual that passes back to the dormant set. Okay, so the kind of high level point of this algorithm is saying, look, we initialize with all our neurons dormant and our empty active set and some residual, which in the beginning is just our labels. We then go through this utility maximization process where every dormant neuron maximizes utility subject to some normal constraint. We then determine the first neuron with the smallest jump time, and we put that neuron into the active set. We then minimize, essentially we're doing this minimization here, we're minimizing the loss, where we are ignoring all the dormant neurons and only minimizing over the active neurons. And I didn't mention this, but it's possible for an active neuron that was previously activated to become dormant again. And if you want to, I think it's not important for this talk so much, but I'm happy to talk about this afterwards. Where basically what can happen is a neuron might have activated, then 3 rounds later, a new neuron comes in, and it actually makes the first neuron want to go back to the origin, become dormant again. So that can happen. Yeah.
Do you think you have a limit where this is asymptotically exact, like AlphaGo to infinity or something like that?
So yeah, this is the conjecture over here, which is I'm describing this iterative, maximization, minimization process that I'm now going to conjecture that in the vanishing initialization, gradient flow for these networks is converging to this process. I am not in this work probably going to prove that, but I can show there exists other works that this framework will encompass, where people have done the hard work of actually showing that gradient flow converges to their algorithm, and I'm going to just show that our algorithm encompasses theirs. Yeah. Yeah.
The neurons are affected through the residual, which is
Yes.
affected by the active neurons. So do the active neurons then influence the dormant neurons, but not vice versa?
Exactly. The active neurons influence the dormant neurons by changing their residual. The dormant neurons do not affect the active neurons. They're small, so the active neurons are unaware, essentially, until one of them pops up, at which point now there's a new active set. Now all of the active neurons have to re-equilibrate, basically.
Is this only for redo activation? Okay, this is for homogeneous activation. If you think about redo activations, you have let's say this piecewise quadratic. Does this jump process just like correspond to jumping between like piecewise quadratic parts of the loss landscape?
So this will be true for ReLU. There does not actually exist if you want to prove this conjecture, I don't know of a setting for ReLU networks where this conjecture has been cleanly proven. I believe this would be the case. We see this kind of being a good proxy even in ReLU settings. But yeah, no, the key thing is not really like whether piecewise linear or not. The key thing is the fact that norms move slower than directions. When you have that behavior at small initialization, then this idea kind of follows. At least 2. In fact, yeah, that is definitely important. At least 2. So 2 over the entire thing. So that means if you're linear, which is degree 1, it's fine because you have one layer and a second layer. So it's degree 2 of the entire thing.
You're not limited to a teacher-student setting that, you know that each neuron can capture like a quanta of the target. If I imagine a complex target where a single neuron, can do anything remarkable, do you think that can still hold? It can somehow capture what it can? And
I think that's the thing I see the value in this framework is by the data. Where does the data come in? It comes into the definition of the utility. And so without kind of prescribing a generative model on the data, I'm saying whatever the kind of solution to this maximization problem, that's where the data comes in. In settings where it's your data is generated from a teacher, we should expect that those fixed points of the solution to this optimization is related to the teacher's neurons. And I'm going to show in some settings where that actually is true. Yeah. Okay, and then lastly, just this process continues alternating between maximization and minimization until, again, either the dormant neurons are empty or residual is 0. So you can kind of, again, along these plateaus is utility maximization. Between them is this fast cost minimization step. Let's quickly, let's go through a couple examples. So this kind of goes to your question about linear networks. So we're going to consider the setting where my nonlinearity is linear. So essentially, each of my neurons produces a rank 1. It has like kind of rank 1 prediction. I'm summing up all these neurons. Let's just again assume that data is whitened, the input output is whitened, and so essentially all that matters is the input covariance is whitened. All that matters is the input output covariance for this problem. I'm going to assume mean squared error. So at initialization, my residual is just the labels. And so if we write out our utility function for a single neuron, remember it's the expected inner product between a neuron and the residual, we can move the parameters out. What we'll find is that it's essentially this bilinear product here. Maximizing that bilinear product subject to a norm constraint is the Rayleigh quotient problem. So we know that essentially what you're converging to is the top left and right singular vector of that input-output covariance. Right. So in this case, for this setting, it's very clear we know exactly what the utility maximization should be doing. It should be saying all neurons want to align to the top eigenvector of this problem, or top singular vector pair of this input-output covariance through data. We can estimate the accumulated utility, which is that path integral, by just using the maximum value. And we can then get an estimate for the time, the first jump time, which will now, the key thing to see is that it depends on your initialization scale and that singular value. And if we look at cost minimization, it's not too hard to show that essentially what the neuron is going to want to do, or a neuron is going to want to do, is that they're going to want to just scale up so that they predict exactly the correct rank 1 prediction here. Give me 1 second. And so what's going to happen after that is that the new utility will be computed with a matrix with 1 degree less for every move that rank component. And now the next top singular vectors is what's going to be learned. So you can kind of see there's this iterative process of learning the top singular vector, scaling, getting a new utility, learning the next one, so on and so forth. And we can get, and from this expression, we can also get the jump time. So here we are on the right. I'm just training this with online, just training this process online, which just means every time I'm sampling from these covariances and training with some learning rate. And we see that the dynamics essentially follow these levels, which are associated with how many singular values have not been learned. And at the jumps is when they move between these levels. Yeah.
The learning rate is kept constant.
Yeah. You had a question?
Yeah. Why in the linear neural case, you are considering the linear combination of the features for the nodes, but for the non-linear case, with rather you can consider every node.
Yeah. So it's a great point. In a linear network, because of that rotational symmetry, really there is a correct basis under which it's a single neuron has been learned. In reality, every neuron is learning a little bit of this. Yeah, a little bit of, so basically every neuron back here, every neuron has some component in each of these different eigendirections, and that component is growing. And so it's the collection of those neurons. And that goes to this question about how does the width and the number start to play a role? In linear networks, it's actually it's a great setting because everything is really simple and we can understand, but it's a bad setting because it has actually way more symmetries than we want, and it makes the problem more complicated. So yeah, your question is a good point.
If you look at like a non-linear network, a linear combination of neuron may activate a single node. Why are you excluding that case out?
I'm not exclude. You're saying for a nonlinear network.
Yeah, for a nonlinear network with larger than 2 or 3 or 4. The linear combination of those neurons may have like the same kind of mode.
Yes.
You kind of do observe that.
Yeah. We definitely observe that. Yeah. So it's really the population of those neurons are kind of activating simultaneously.
How do they break?
Right now, it hasn't. This is like, I would say 60% done. So I actually think this is a very important question that I'm trying to understand more deeply. Yeah. Okay. Any other questions about this? So just right off the bat, I guess the point here is this maximization minimization problem that process that I described. One way to understand it is it's literally doing SVD on your input output covariance. Read-delete, one singular vector at a time. And this matches very well with what we know in the literature, where in 2020, this paper Lee et al. Proved that essentially any 2-layer matrix factorization problem, so this would allow for X with X be unweighted, essentially gradient flow with an infinitesimal initialization is equivalent to a simple heuristic rank minimization algorithm, where essentially, I don't know if that's really the right wording, but essentially what's happening, this is their algorithm on the left. What they do is they start with some gradient of loss with respect to some residual, let's say. You learn the top eigenvector of that residual, you add it to a growing set, and then you do gradient descent with that growing set, getting a new residual and repeat the process. So right off the bat, you can really see that this alternating gradient flows framework that we're talking about is like, this is the maximization step, where now you see that the eigenvector is maximizing this utility. That's why you get this top eigenvector. This is your active set, and this is your minimization, doing gradient descent. This alternating gradient flows point is that you're doing a gradient ascent in this step and a gradient descent in this step. Okay, another setting that we can look at is a diagonal linear network. Here, it's essentially just constraining that first layer to being a diagonal matrix, such that your linear network is like kind of coordinate aligned or has some coordinate preference. This is a setting that's been used in the literature. If you're interested in implicit bias works, this has been a setting that has been like massively explored and very great analysis in the implicit bias work has been done in this minimal model. And we consider the gradient flow dynamics with some initialization where essentially we set B to be 0 and U, the first layer, to just be alpha, from alpha comes to all ones, and we're going to think about what happens when we take alpha to 0. The utility for this network is now for each of these neurons, we can define the utility, essentially the gradient of loss with respect to that coefficient, beta, for, gradient of loss with respect to either the I coordinate of beta, which is just the product of U and V. We can actually, in this case is super special. It's a setting where we don't need to estimate or approximate anything. We can actually analytically solve for the accumulated utility, and you get some kind of complicated equation. And if you look at an existing algorithm in the literature, what we'll find is that in the limit that alpha goes to 0, the solution that alternating gradient flows gives converges to the solution found in the literature. And again, these 2 steps can be kind of seen in this algorithm. So here's just some pictures of those dynamics happening. Basically, what I'm doing is I'm plotting the loss here on the right, and over here I'm plotting the value of the coefficients of U times B. The theory is the dotted lines, and we can see the jump times predicted by their algorithm and our algorithm are identical. So again, what's happening here is I'm using a coordinate line covariance, and so it's like one coordinate comes up, and then another, and so on. But it gets much more interesting if you allow for an unaligned covariance of your input. Now, when one coordinate comes up, when the next coordinate comes up, those 2 coordinates change. So actually, in this setting, you can find that you can get that behavior I told or alluded to earlier, where a coordinate can activate and that can drive another coordinate back to the origin. That's saying that now each of these coordinates is a neuron, and they can go active and then back to dormant. in the last 5 minutes, I'm just going to quickly go to, okay, so those were two settings that exist in literature. And we show that this algorithm, essentially, or this framework encompasses those settings. And now I want to talk about a setting that there is no explanation for in the literature, at least as far as I'm aware of. So the setting is, we're going to train.
Just the comment, we have explanation without any equilibrium, not for the dynamic.
Yeah, exactly. Yes. So, yes, there are explanations of. So this is great. So, essentially, I'm going to look at a two-layer quadratic network. So, also in the previous two settings, I was using linear, nonlinear. I want to use a nonlinear. I want to use something slightly more complicated. So, I'm going to look at a setting where my nonlinearity is quadratic or square, and I'm going to have again all these neurons, and they all are computing some function. What is the task? The task is, I want to train a network to do modular addition. So I want to train a network on these p-squared possibilities to learn, essentially, to do modular addition. Right? Yeah.
In this case, what's your x? And you can change like your inputs. It could be like the jumps.
So are you asking how x?
Yeah, how it depends on the structure of your data.
Yeah. So x is going to change essentially the value of this, and that's going to change your utility. It's going to change your jump times. It's going to change your levels. It's going to change everything.
Yeah, because in graph it depends a lot on your needs.
Yeah. So it's all the utility is the thing that where the data comes in, and that determines the jump times and the levels. Yeah. Okay. So just back to the setting. This is a setting that's been really popular in the last couple of years as a setting for studying emergent behavior or grokking, which is this phenomena of generalization and training error being kind of misaligned. And I think there's two phenomena in these settings. This phenomena I want to talk about is that when you train a network to do modular addition, this type of network to do modular addition, what people have found is that these neurons specialize to individual frequencies. They basically all specialize to learning cosine waves. And they're
no. This is true for rebels, less true for
no, it's I suggest going to this paper. It's true for quadratic and Rayleigh, in fact, but it's actually much easier, and our proofs rely on quadratic. Yeah. So the idea, though, is that essentially, how do we even encode this as a problem? What does it mean to teach a network to do modular addition? Basically, we treat each of these numbers as a one-hot vector, and we give it two one-hot vectors A and B, and then we try to have the network predict the correct kind of one-hot vector to represent A plus B mod P, whatever P is. And again, kind of what's found in literature is that one solution to this, and a solution that seems to align with what people have seen empirically, is that these neurons will specialize to certain frequencies, different frequencies, and then they'll kind of add themselves together to constructively interfere at the right place and deconstructively interfere at the wrong places. So that they essentially put a 1 where the correct A plus B is, mod P, and they put a 0 everywhere else. So just to see that through training, we look at the loss curve through training, and right here what I'm just doing is I'm plotting a vector, one of the weight vectors from each neuron. So every horizontal part here is a neuron, and I'm just plotting, I think, just this W, one of their 3 vectors. Each neuron has 3 vectors, U, V, and W. I'm plotting just W. And what you'll see is through training, these vectors start kind of random, and then on the right, I'm just plotting the frequency spectrum. And what we see is that essentially they kind of suddenly kind of collapse to a certain frequency. And there's kind of, in terms of the loss, we see like in the beginning, there's kind of a plateau. First, the network learns to predict the mean. And then there's kind of like a wavy line going down. It's actually, this was cherry picked from an earlier figure when I thought this was really striking saddle. And then I realized it's not. So let me get to why. So I talked about this problem as being encoded with the one hot vector. And in general, when you encode this problem with a one hot vector, essentially you get that, you learn that first saddle, you learn the mean, and then essentially you just, all the frequencies that rise and emerge simultaneously. You learn all these frequencies simultaneously. However, you could consider just an arbitrary encoding of this problem or a correlated encoding. So one way to think about this one hot encoding, which is commonly used in the literature, is I take I have a one on my 0th index and 0 everywhere else. And I just kind of cyclically permute that vector to represent each of the numbers. So 2 would be taking this vector here and cycling it by a shift of 4 or a shift of 8. And the frequency spectrum of this vector is uniform across all frequencies, right? And so one way to think but what happens if we instead did some kind of non-uniform spectrum and shifted it to represent our data? Then you will find very striking saddle-to-saddle behavior. And what essentially high-level picture I'm going to show you is that idea I said earlier, where gradient descent is learning to do SVD. Essentially, in this problem, learning to do the discrete Fourier transform, one frequency at a time. I've basically broken the symmetry in this problem that is due to this encoding. And with this encoding, now there is a dominant frequency that it learns first, then the next one, and so on and so forth. And we can prove that. We can actually show that, again, for the quadratic nonlinearity, you can show that the directions that maximize the utility are aligned with the dominant frequency of your encoding.
So I would still think that even in the usual encoding, there will be some random weights that are better aligned, and these will pop up first. Shouldn't you see that at some crazy small variance, maybe?
And that's what we see here. Yeah.
This is with the standard encoding.
This was with a standard encoding.
Oh, okay.
And that's why I said I cherry-picked it. Because when I started this, I was like, this is it. And then I realized that, no, if I allowed my encoding to change, I could make this happen every single time, the same order of saddles.
And so what happened at the top?
Right at the top, it's essentially I have a very wide network, and the randomness isn't playing a big role. I had to play around quite a bit to see that variation. Yeah. So one way to again think about this distinction here is like if in a linear network, if my data was whitened, essentially it would learn to do SVD. All the singular vectors would be learned simultaneously. You would see no saddle process. It's still happening kind of under the hood, but it's happening all at the same time, so you don't see it. You can't see it disentangled. But by changing our encoding, we get access to it. So yeah, basically the proofs here are going as we show that the cosine waves are the unique critical points that maximize the utility, the unique directions that maximize the utility. Then we get something quite weird, which is that when we try to do the second step, we find that essentially the neurons, they grow in norm, but they actually have to collaborate together. You have to have at least 6 neurons that work together in order to remove one frequency from the problem. It's very weird, and it's essentially about trying to have them separate their phase shifts so that they essentially, in expectation, average themselves out. It's a weird thing that you wouldn't see in a linear network where essentially one neuron can learn one SVD and one singular vector. Here, you need a group of neurons to collaborate in order to remove a frequency. And then when we put that together, we get kind of it's not as precise as the other settings, but we get kind of a good approximation to the levels and the jump times. When we see some interesting behavior, we see that often right after a cost minimization, we see large spikes or instability in the loss. And we could train these with Atom, and it would just smooth those out, but it still would see the same sequence of saddles. Another thing we also observe is that the network consistently uses about 6 neurons to fit each frequency. Even if it has access to many, many more neurons, it still uses about 6, which is the minimum number it can use. This is kind of hinting at this idea that there is actually like an implicit sparsity bias, where it's trying to use as few neurons, active neurons, as possible. Okay, so I gave you 3 examples of this framework. Future directions are first finishing it, and then there's some ideas about how do we expand this to other settings that might exist in literature, like multi-index models. How can we extend this to deeper networks, because this is constrained to these 2-layer networks, or remove the homogeneity assumption? And then can this even be used as like an optimization algorithm, right? An optimization algorithm that does feature learning that's not using SGD. So I think there's a lot of room for thought in exploring this direction. I gave you a lot of information, and I'm 2 minutes over, but thank you.
The jump in general has this kind of interaction with spaces. I was wondering, is that Which saddle do we are, is that like ordering which like?
Yeah, it will in some cases. For example, in the linear network, the jump time won't matter. Meaning, or this coordinate line setting. Essentially, each of these jump times is predetermined at initialization. In other settings like this, you actually have to determine the right jump time. You need to first figure out which saddles you visited first. So you have to construct it iteratively. Yeah.
Can you explain, maybe show the slide again, how you get the multiple channels from the definition?
Yeah.
Are you forcing the neurons to not be monosymmetric?
I'm not, there's no like, this is just gradient dynamics.
So the previous thing, the one, yeah, this one, the bottom. Yeah.
Yeah. So what I'm doing here is just changing the way I encode the data, not changing anything else about the architecture or the problem. I'm just saying, you know, we're trying to learn modular addition. So how do I represent an integer? I want to represent it as a vector, and I could represent it as a one-hot vector, or I could represent it as a cyclic permutation of some base vector. And so that's what the bottom is doing. For example, if I made this the all ones vector as my template, then essentially the best you would just predict the mean and you'd be done. There's no so the number of saddles in this case has to do with the number of frequencies needed to represent that vector. So if this base vector was a cosine wave, there would only be 2 saddles. Learn the mean and then learn that whatever that frequency for that base vector is. Yeah. Cool. I'll be around, so thank you so much.